Okay, moving on to polarity and electronegativity. Let's talk about those polar covalent bonds we brought up before. Remember that electronegativity is defined as an element's ability to attract electrons to itself. Things that are electronegative attract electrons strongly and they hold electrons tightly. And sometimes they tend to take electrons. Electropositive atoms attract electrons weakly and they may give up electrons. Normally, we think of things in terms of electronegativity, and if something is electronegative. Things that are not electronegative are electropositive. Electronegativity ultimately is used to help us predict the relative reactivity of compounds. So understanding trends of electronegativity is generally important because it's going to go back to how reactive something is, which we'll be talking a lot about in organic. Here's a table to remind you some of the trends in electronegativity. Generally, you see that electronegativity increases from left to right across the periodic table, across the periods, and from bottom to top within a group. Meaning that fluorine is generally the most electronegative element. And as you go down, you lose electronegativity. So when you have two atoms with different electronegativities, they're going to share electrons unequally. Even if they're forming a covalent bond and they're sharing, this results in a polar covalent bond. And the greater the difference in electronegativity, the more polarized the bond. So our example here with HF, hydrogen fluoride, you can see, though this forms a covalent bond, not an ionic bond, the fluorine is strongly negatively charged. It takes on almost all of that electron density, whereas the hydrogen is partially positive charged. It gives away most of its electron density. And if we refer back to the table, you can see the difference in their electronegativity. Fluorine, again, has an electronegativity value of 4, while hydrogen only has a 2.1. We can draw this polarity using something called a dipole moment vector. This vector is going to just show the general trend of polarity. It's going to indicate the dipoles. This just means the poles, the positive end and the negative end, the poles of a molecule. This is done by drawing this arrow in which the positive end has kind of a plus shape. And the negative, the area that the electrons are moving to, is where the arrowhead is. Now, this dipole moment view is kind of a simplification of the reality of a molecule. Molecules have a wide spatial distribution of charge. It's not just one positive end and one negative end. It's not really poles. Instead, something like this electrostatic potential map, this ESP map, is going to better show kind of the distribution of the charge over the molecule. This shows it via colors, where the blue region is the area that's partially positive and lacks electron density, and the big red region is the negative area that has excess electron density. So again, we would draw the dipole moment vector like this, but this map kind of showcases the electron density better. It shows it using size and color. Here's another example. This is our F2 molecule. Now we talked about how polarity is caused when you have electronegativity that is different between the two bonded elements. In this case, we have fluorine bonded to fluorine. So even though fluorine is very, very electronegative, when it's bonded to another fluorine, they equally pull on each other. And so in this case, you do not have a polar molecule. You have a very evenly pulled density, which you can see with our electrostatic potential map again. In this case, there's no positive region and there's no negative region, and that's because the electron density is shared equally between the fluorines. So here's a table if you want to kind of review some common bonds that we will look at and their dipole moments. So we talked about HF. This is a bond between a hydrogen and a fluorine. And here's other common types of bonds we'll look at, including carbon-oxygen bonds is a very typical one we'll see in organic chemistry, or hydrogen-nitrogen bonds. These numbers here are associated with the differences in electronegativity between the two elements. So the greater the difference, the greater the dipole moment. Like we said, between hydrogen and fluorine, there is a very large difference. And so there's a very large dipole moment, meaning that there's a big difference of positive and negative region. But if you look at something like carbon and oxygen, like I brought up, the dipole moment is very small. These are very similar in their electronegativity, and so the electron density is shared pretty equally between these two things.